This call is now being recorded.
Okay. So the chapter number 6, the name of the chapter is Bending Stresses in the Beam. So in this particular chapter only we have to calculate only one parameter by using the only one formula, and that particular parameter is called as the bending stresses, which will be either represented by the sigma or it is also represented by the sigma b. Why b is there? Because it represents the bending stresses. So in the last chapter, whatever we have covered, that is SFD and BMD, in that we have calculated the shear force calculation, we have calculated the bending moment calculation, but we are not calculated any type of stress. Maybe we have not calculated shear stress, we have not calculated the bending stress. But what happen when any beam, maybe the cantilever beam is there, maybe simply supported beam is there, or maybe the overhanging beam is there, if that particular beam is subjected to the number of loads, maybe the beam is subjected to the point load, UDL, UVL, couple. So what happen, due to the number of loads applied on that particular beam, it is subjected to the shear force and the bending moment. But as far as the chapter number 6, now here only we have to focus on the bending concept only. If the beam is subjected to the number of forces, due to the number of forces are applied on that particular beam, the bending of the beam is taking place. Bending of the beam is taking place means the bending moment is developed in that particular beam, and due to that particular bending moment, that beam is subjected to the bending stress also. So if I have to calculate the bending stress induced in that particular beam, the first requirement is that we have to calculate the bending moment in that particular beam, and by using that particular bending moment I can calculate the bending stress induced in that particular beam. How to calculate the bending moment? In the last chapter we have discussed the bending moment at point A, B, C, D. That bending moment, how to calculate, we have discussed in that particular last chapter. But now here, in case of a bending stress of that particular beam, here we have to focus only on the standard conditions. Which are that particular standard conditions? If you go through this particular content of this particular chapter, that is syllabus, that is we have to start with the basic introduction part, how to calculate the bending stresses, how the bending moment will be used for the bending stress calculation. Then we have to discuss about very important concept, theory of pure bending. This is one theoretical concept which we have to discuss. What is meant by the theory of pure bending? Because based on this particular theory of pure bending, some MCQ based questions are also there. Then second point is the assumptions. So when we are starting with the torsion chapter, in that particular torsion, theory of torsion, assumptions made in the theory of torsion. Similarly, we have to consider some assumptions also in case of a bending stress formula also. Which conditions that beam has to satisfy, that represents the assumptions made in the theory of pure bending. Then sign conventions again we are going to discuss here. Then bending stress distribution diagram. This point is very important. Like SFD and BMD, what we have done? We have done SF calculation, we have done BM calculation, and then that calculation is represented in the form of diagram. That diagrams are called as a shear force diagram and the bending moment diagram. Similarly, in bending stress, in this particular chapter, what we have to do, we have to calculate the bending stresses, and that bending stresses can be represented in the form of diagram. That diagram is called as a bending stress distribution diagram. So here maximum we have to focus only on the two types of beam. One is the simply supported beam and another is the cantilever beam. So I have to represent the bending stress distribution diagram for the simply supported beam and the bending stress distribution diagram for the cantilever beam. So in this particular chapter, we are not having the overhanging beam related to the bending stress calculation. Only we have to study the simply supported beam and the cantilever beam only. Then flexural formula, bending stress formula, we are having one small derivation, and that derivation is related to the bending stress calculation. If I have to calculate the bending stress induced in that particular beam, first requirement is that we have to derive one formula. We have to derive one formula, and that formula is called as a bending stress formula. So which formula we have to derive actually? Let us see here. M upon I is equal to sigma upon Y is equal to E upon R. So this is the bending stress formula. M upon I is equal to sigma upon Y is equal to E upon R. We have to derive this particular formula first, because by using this particular formula only we have to go for the calculation of the bending stresses, and then we have to solve the numericals based on the different types of the sections. Maybe you have studied I section is there, symmetrical I section, unsymmetrical I section, T section, inverted T section, rectangular section, circular section, hollow circular section. There are different types of the sections are there. For such different types of the sections, we have to calculate the bending stresses. So once that particular formula is to be derived, then how to use that particular formula for the bending stress calculation, that we will see that time only. But you just remind this particular formula, M upon I is equal to sigma upon Y is equal to E upon R. We have to derive this formula only, and by using this single formula only, we have to go for the calculation of the bending stresses. Okay, so this is about the syllabus content which we have to cover in this particular bending stresses in the beam. Now, if I have to start with this particular introduction, why we have to go for the bending stress calculation? So here, what I will do, I will take some standard cases. In this particular chapter, only we have to study the standard cases. So the first case, let us see. Simply supported beam. Only two types of the beams we have to study in this particular chapter. Simply supported beam. There are two standard cases. Let us see. Simply supported at the two ends, subjected to the point load at the center. A, B, C. This is the one case. Second, again simply supported beam, again supported at the two ends, point A, point B, and it is subjected to the UDL. It is subjected to UDL on entire span, that is W kilonewton meter. This is for the simply supported. And second beam is cantilever. Again, here we have to study the two cases. Cantilever beam. One end is fixed, another end is free, subjected to the point load W at the free end. And one more cantilever beam. One end is fixed, another end is free, and subjected to the UDL. W kilonewton meter. This is point A, this is point B, this is point A, and this is point B. So these are the four conditions. Based on this particular four conditions only, we have to calculate the bending stresses. So what is the first type of the beam? Simply supported. In simply supported beam, there are only two standard conditions. That is, first one is a simply supported beam subjected to the point load at the center. So if you go through the figure number 1, in that the beam is supported at point A, the beam is supported at point B, and at the center point, one point load is applied. So what happened? Due to the point load applied at the center, the bending of the beam is taking place in the downward direction. What happened? Whatever this particular curve is represent, this curve represents the bending of the beam is taking place in the downward direction. Why the bending is taking place? Because whatever this P amount of force is applied at the center point, it is applied in the downward direction. So whatever the bending is taking place, that bending is taking place in the downward direction. So due to the bending is taking place in the downward direction, what happen? This particular beam is subjected to the some amount of bending stress. This particular beam is subjected to the some amount of bending stress, which is represented by the sigma b, and this bending stress I have to calculate for this particular type number 1. If I have to calculate the bending stress, initially I have to calculate the bending moment as a capital M at that particular point C. As the point load is applied at the center point or at the point C, so initially I have to calculate the bending moment as a capital M at point C, and by using this particular bending moment I can easily calculate the bending stress as a sigma, because we are having the formula M upon I is equal to sigma upon Y is equal to E upon R. जर मी M काढला असेल, moment of inertia I, we can easily calculate. Sigma is the unknown, Y represents the distance of CG. So before calculating the bending stress, my first requirement is that I have to calculate the bending moment as a capital M. And now in the figure number 1, what happened? The point load is applied at the center, due to which the bending is taking place in the downward direction, which is represented by this particular curve. So for this particular first case, this M formula will be different. If I have to calculate the bending moment capital M for the simply supported beam subjected to the point load at the center, this M formula will be different. Now second case, again the simply supported beam is there, but the type of load is changed. What is that? The beam is supported at the point A and B, and it is subjected to the UDL on entire span. So due to that particular UDL also, again the bending is taking place in the downward direction. What happened? This UDL, it is spread on the entire span, and that particular UDL is also acting in the downward direction. So due to that, the bending is also taking place in the downward direction. Again, here I have to calculate the sigma b as a bending stress, but before that sigma b calculation, the first requirement is that I have to calculate the bending moment, which is represented by the capital M. And for this particular case, what is the case number 2? The simply supported beam with UDL on entire span, the formula for M will be different. The formula for the M for the case number 1, that is simply supported beam subjected to the point load at the center, M formula for the different for the case number 1. Then M formula will be the different for the case number 2, in which the simply supported beam is there and it is subjected to the UDL on the entire span. Similarly, in case of a cantilever beam, what is the construction of the cantilever beam? One end is fixed, another end is free. And in case of a cantilever beam, the first figure tells that standard case, one end is fixed, another end is free, and the point load is applied at the free end. So in that case, how the bending is taking place, you can see here. So whatever the bending is taking place in the downward direction, that can be represented by the curve. So what happened? Again, if in case of a cantilever beam, if this W amount of load is applied at the free end, due to that particular W amount of load, the bending is taking place in the downward direction, and due to that, I have to calculate the bending stress as a sigma. I have to calculate the bending stress as a sigma. But before that, first of all, my requirement is that I have to calculate the bending moment as a capital M. Again, for this particular case number 3, that is simply cantilever beam with one end is fixed and another end is free, and the point load is applied at the free end. Again, this bending moment formula will be different. And similarly, for the last case, the cantilever beam subjected to the UDL on entire span. So due to that particular UDL, again the bending is taking place in the downward direction. Again, the bending is taking place in the downward direction. Again, if I have to calculate the bending stress in this particular case number 4, first requirement is that I have to calculate the bending moment as a capital M. So that means in all the 4 cases, in case of a simply supported beam subjected to the point load, simply supported beam subjected to the UDL. Similarly, cantilever beam subjected to the point load, and the cantilever beam subjected to the UDL. In all the four cases, I have to calculate the bending stress induced in that particular beam. But to calculate that particular bending stress, first requirement is that I have to calculate the capital M as a bending moment. Before calculation of bending stress, first requirement is that to calculate the bending moment as a capital M. If I have to calculate this capital M for the cantilever beam subjected to the point load, formula will be different. Please keep in mind. If I have to calculate the bending moment as a capital M for the simply supported beam subjected to the UDL, again the formula will be different. In case of a cantilever beam subjected to the point load at the free end, if I have to calculate the bending moment as a capital M, again the formula will be different. And last case, if I have to calculate the bending stress for the cantilever beam subjected to the UDL, but before that I have to calculate the bending moment, again the formula will be different. So for all the four cases, your M formula will be different because conditions are different. एका ठिकाणी पॉइंट लोड आहे, एका ठिकाणी युडीएल आहे, परत कॅन्टिलिव्हर मध्ये एका ठिकाणी पॉइंट लोड आहे, परत त्याच्यावर युडीएल आहे. जर लोड जर व्हॅरी झाला असेल तर त्याच्यावरचा बेंडिंग मुवमेंट पण 100% काय होणार आहे, व्हॅरी होणार आहे. जर बेंडिंग मुवमेंट व्हॅरी होत असेल तर त्याच्यामध्ये इंड्यूस होणारा बेंडिंग स्ट्रेस पण काय होणार आहे, व्हॅरी होणार आहे. Therefore, we have to calculate the bending stress to the each and every case. मग त्याच्यामध्ये आपल्याला ह्या चॅप्टर मध्ये किती केसेस स्टडी करायच्या, तर ह्या 4 केसेस स्टडी करायच्या. त्यामध्ये कुठल्या, एक सिम्पली सपोर्टेड बीम सब्जेक्टेड टू द पॉइंट लोड अँड युडीएल, अँड सेकंड कॅन्टिलिव्हर बीम सब्जेक्टेड टू द पॉइंट लोड अँड द युडीएल. चारही बीम साठी आपल्याला एकच स्ट्रेस काढायचा आहे, तो म्हणजे कुठला, बेंडिंग स्ट्रेस. पण प्रत्येक बीम मधला बेंडिंग स्ट्रेस जर आपल्याला फाइंड आउट करायचा असेल तर त्या बीम मधला पहिल्यांदा आपल्याला बेंडिंग मुवमेंट कॅपिटल एम हा आपल्याला काय करायचा आहे, फाइंड आउट करायचा आहे. जर तो कॅपिटल एम फाइंड आउट करायचा असेल तर प्रत्येक बीमला, प्रत्येक कंडिशनला बेंडिंग मुवमेंट फॉर्म्युला काय आहे, तर वेगवेगळा आहे. जर बेंडिंग मुवमेंट फॉर्म्युला जर वेगवेगळा असेल तर त्या चारही बीम मध्ये किंवा या चारही कंडिशन मध्ये इंड्यूस झालेला बेंडिंग स्ट्रेस पण काय असणार आहे, वेगवेगळा असणार आहे. Therefore, we have to study this particular chapter in order to find the bending stress in that particular beam subjected to different types of loading. मग कॅन्टिलिव्हर मध्ये 2 टाइप, एक पॉइंट लोड, एक युडीएल, आणि सिम्पली सपोर्टेड मध्ये पण 2 पॉइंट, एक पॉइंट लोड आणि दुसरा युडीएल. So this is our requirement, that is to calculate the bending stresses induced in the beam if that beam is subjected to the bending moment. जर त्या बीम मध्ये बेंडिंग मुवमेंटच इंड्यूस होत नसेल, जर सिम्पली सपोर्टेड असू द्या किंवा कॅन्टिलिव्हर असू द्या, जर ह्या दोन्ही बीम मध्ये जर बेंडिंग मुवमेंट जर डेव्हलप होत नसेल तर वी कॅन डायरेक्टली से दॅट देर इज नो एनी बेंडिंग स्ट्रेस. तर मुवमेंट, बेंडिंग मुवमेंटच होत नसेल तर त्या बीम मध्ये बेंडिंग स्ट्रेस हा इंड्यूस होणार नाही. बट ऍज द बीम्स आर सब्जेक्टेड टू द लोडिंग, if it is subjected to the loading 101%, there may be possibility of bending moment. If the beam is subjected to the bending moment 101%, it is subjected to the bending stress also, and that we have to calculate. So this is the basic introduction related to the bending stress calculation. Okay, so this is about the introduction part. Now we'll discuss about the pure bending of the beam. Why this particular concept we have to consider pure bending of that particular beam, or it is also called as a simple bending. It is also called as a simple bending. What is meant by the pure bending? First of all, I will give the simple definition for the pure bending of the beam. What is that particular definition? When beam is subjected to the constant bending moment. Listen the definition carefully. When beam subjected to constant bending moment and no shear force at that portion. If beam is subjected to the constant bending moment and no shear force at that portion, that concept is called as a pure bending. Means while calculating the bending stress in any type of beam, the effect of shear is totally neglected. बघा, एखाद्या बीमवर जर आपण पॉइंट लोड किंवा युडीएल जर ऍक्ट झाला तर त्या बीम मध्ये शियर फोर्स पण इंड्यूस होणार आहे आणि बेंडिंग मुवमेंट पण इंड्यूस होणार आहे. दोन्ही पॅरामीटर इंड्यूस होणार आहेत. पण आपली रिक्वायरमेंट काय, वी हॅव टू कॅल्क्युलेट द बेंडिंग स्ट्रेस ओनली. बेंडिंग स्ट्रेस काढताना आपल्याला शिअरचा इफेक्ट हा टोटली निग्लेक्ट करावा लागणार आहे किंवा इट इज इक्वल टू 0. Means while calculating the bending stresses in any type of beam, the effect of shear is totally neglected or it is equal to 0. जरी त्या बीम मध्ये शिअर फोर्स इंड्यूस होत असेल, शिअर स्ट्रेस इंड्यूस होत असेल, पण बेंडिंग स्ट्रेस काढताना शिअर फोर्सचा इफेक्ट आणि शिअर स्ट्रेसचा इफेक्ट आपल्याला काय करायचा आहे, निग्लेक्ट करायचा आहे. म्हणजेच तो इफेक्ट काय करायचा आहे, आपल्याला 0 करायचा आहे. And that concept is correlated with this particular pure bending and the simple bending. So what is that particular definition indicate? Pure bending means pure bending of the beam. When the beam is subjected to the constant bending moment, when beam is subjected to the constant bending moment, at that portion there is no shear force, or at that portion shear force is equal to 0. That concept is called as a pure bending. For that purpose, here one figure is represented. What that particular figure indicates, you can see one simply supported beam is there. So here, yes, okay. So in this particular figure, in order to understand the concept of pure bending, I have considered one figure. What that particular figure indicates, one simply supported beam is there. So this is point A, that is one support of the simply supported beam, another point D, another support of the simply supported beam, and this particular simply supported beam is subjected to the 2-point loads. This is first W, another second W. That is one simply supported beam is there. It is supported at the two ends. That is at point A, it is supported. At point D, it is supported, and at point B, the W amount of point load is applied. At point C, another W amount of point load is applied. That means this is the loading diagram, and below this loading diagram I have drawn the SFD. You can see here M1 SFD is there, and below that SFD BMD means bending moment diagram is there. That means if the simply supported beam is subjected to the 2-point loads of the W, their SFD diagram and their bending moment diagram I have drawn here. And as per the pure bending definition, as per the pure bending definition, the beam is subjected to the constant bending moment. The beam is subjected to the constant bending moment. Now focus on the portion B to C. In this particular figure, only we have to focus from the portion B to C. You can see in case of a bending moment diagram, point B is there, point C is there, point B and point C. In portion B to C, your bending moment is constant. In case of a bending moment diagram, only focus on BMD, don't focus on SFD. Focus on BMD. In portion BC, your bending moment is constant. बघा ह्या खालच्या पॉइंट ए पासून पॉइंट ए आणि बी इन्क्लाइंड लाईन ने जॉईन केलेत, पॉइंट बी आणि सी हॉरिझॉन्टल लाईन ने जॉईन केलेत, आणि परत पॉइंट सी आणि डी परत काय केलेत, इन्क्लाइंड लाईन ने जॉईन केलेत. पोर्शन बी टू सी तुमचा बेंडिंग मोमेंट काय आहे, कॉन्स्टंट आहे. ऍज पर द डेफिनेशन ऑफ प्युअर बेंडिंग, वेन द बीम इज सब्जेक्टेड टू द कॉन्स्टंट बेंडिंग मोमेंट, म्हणजे बी आणि सी मध्ये बेंडिंग मोमेंट कॉन्स्टंट आहे. पण हाच पोर्शन जर आपण शिअर फोर्स डायग्राम मध्ये बघितला तर बघा, शिअर फोर्स डायग्राम मध्ये हा पॉइंट बी आहे आणि हा पॉइंट सी आहे. In case of a shear force diagram, this is point B, this is point C. Whether that shear force is maximum or whether shear force is 0, please tell me. Bending moment diagram मध्ये from portion B to C bending moment हा constant आहे, पण तोच पोर्शन BC पोर्शन जर आपण shear force diagram मध्ये जर बघितला तर shear force diagram मध्ये BC पोर्शनला shear force हा मॅक्सिमम आहे का मिनिमम आहे का 0 आहे?
0
आहे बघा. दिसतंय पोर्शन बीसी हा एसएफडी डायग्राम मध्ये 0 लाईन वर आहे, पण बेंडिंग मोमेंट डायग्राम मध्ये तोच पोर्शन बीसी काय इंडिकेट करतोय तर कॉन्स्टंट बेंडिंग मोमेंट. म्हणजे ज्या वेळेस आपल्याला बेंडिंग स्ट्रेस फाइंड करायचा असतो त्यावेळेस त्या ठिकाणचा शियर फोर्सचा इफेक्ट किंवा शियर स्ट्रेसचा इफेक्ट आपल्याला इज इक्वल टू काय करायचा आहे, 0 कन्सिडर करायचा आहे. आणि तोच कन्सेप्ट आपण ह्या प्युअर बेंडिंग किंवा ह्या सिंपल बेंडिंग मध्ये करतोय. तर त्याची काय डेफिनेशन आहे, डेफिनेशन काय सांगते बघा, व्हेन बीम सब्जेक्टेड टू कॉन्स्टंट बेंडिंग मुवमेंट अँड नो शियर फोर्स ऍट that portion, that concept or that portion is called as a pure bending. मग बघा, in case of a bending moment diagram, the portion BC represents the constant bending moment, but if I will observe the same BC portion in case of a shear force diagram, in case of a shear force diagram at portion B to C, your shear force is 0, means this particular beam is subjected to the प्युअर बेंडिंग ओनली. जिथं बेंडिंग मोमेंट कॉन्स्टंट आहे त्याच पोर्शन मध्ये जर शियर फोर्स 0 असेल तर दॅट बीम इज सब्जेक्टेड टू द प्युअर बेंडिंग और दॅट पर्टिक्युलर बीम इज सब्जेक्टेड टू द सिंपल बेंडिंग. मग ह्याच्यावरचा 100% एक एमसीक्यू क्वेश्चन तुम्हाला विचारलेला असतो, व्हेन बीम इज सब्जेक्टेड टू द प्युअर बेंडिंग. मग खाली 4 ऑप्शन दिलेले असतील, शियर फोर्स मॅक्सिमम, शियर फोर्स मिनिमम, बेंडिंग मुवमेंट कॉन्स्टंट, बेंडिंग मुवमेंट 0. मग त्यातला तुम्ही कुठला ऑप्शन सिलेक्ट केला पाहिजे तर बेंडिंग मुवमेंट इज कॉन्स्टंट किंवा शियर फोर्स इज 0 असे जर ऑप्शन दिलेले असेल तर त्याच्यापैकी जर शियर फोर्स ऑप्शन दिला असेल तर त्या ठिकाणी शियर फोर्स हा 0 असतो, हा ऑप्शन आपल्याला सिलेक्ट करावा लागेल. जर बेंडिंग मुवमेंटचे जर ऑप्शन दिलेले असेल तर त्या ठिकाणी बेंडिंग मुवमेंट हा मॅक्सिमम असतो किंवा बेंडिंग मुवमेंट हा कॉन्स्टंट असतो, तोच ऑप्शन तुम्हाला काय करावा लागेल, सिलेक्ट करावा लागेल. Therefore, if your beam will satisfy this particular condition, which condition? The bending moment is maximum where shear force is 0. बघा, पॉइंट बी टू सी बेंडिंग मोमेंट काय आहे, मॅक्सिमम आहे. पण तेच 2 पॉइंट द शियर फोर्स डायग्राम मध्ये जर आपण बघितले तर बी टू सी शियर फोर्स काय टोटली 0 आहे. म्हणजे your bending moment is maximum but shear force is 0. If this condition will be satisfied by that particular beam, then I can say that the beam is subjected to the pure bending, or it is also called as a simple bending. So once again repeating, when the shear force is 0 but bending moment is maximum, that particular concept is called as a pure bending. This is the definition number 1. Second definition, when beam is subjected to the constant bending moment and there is no any shear force in that particular portion, जिथं bending moment constant आहे पण shear force 0 आहे, that concept is called as a pure bending. And in order to satisfy this particular definition, we have considered this BC portion of BMD and B2C portion of SFD. In case of a BMD, the BC portion represents the constant bending moment, and in case of a SFD, that BC portion represents the 0 shear force, means our condition is satisfied. Therefore, directly I can say that this particular beam is subjected to the pure bending only. म्हणजे ह्याच्यामध्ये फक्त बेंडिंग मोमेंटच आहे, शियर फोर्सचा इफेक्ट आणि शियर स्ट्रेसचा इफेक्ट हा टोटली आपण काय केलेला आहे, निग्लेक्ट केलेला आहे. त्यामुळे तुम्ही जर तो मोठा फॉर्म्युला बघितला, एम अपॉन आय इज इक्वल टू सिग्मा अपॉन वाय इज इक्वल टू ई अपॉन आर, ह्या फॉर्म्युल्यामध्ये पण शियरचा इफेक्ट कुठंच दिसत नाही. आय म्हणजे काय सांगतोय, मोमेंट ऑफ इनर्शिया, एम म्हणजे काय सांगतोय, बेंडिंग मोमेंट, सिग्मा म्हणजे बेंडिंग स्ट्रेस, वाय मीन्स डिस्टन्स ऑफ सीजी, ई काय सांगतोय, कॉन्स्टंट पॅरामीटर यंग्स मॉड्युलस ऑफ दॅट पर्टिक्युलर बीम, अँड आर म्हणजे काय सांगतोय तर रेडियस ऑफ द कर्वेचर. पण ह्या टोटल फॉर्म्युल्यामध्ये तुम्हाला शियर फोर्सचा इफेक्ट किंवा शियर स्ट्रेसचा इफेक्ट कुठंच दिसत नाही. मीन्स वी कॅन डायरेक्टली से दॅट द बीम इज सब्जेक्टेड टू द प्युअर बेंडिंग ओनली. And that definition we have discussed by using this particular SFD and the BMD. The portion BC is subjected to the constant bending moment in BMD, but same portion BC is subjected to the 0 shear force in case of a SFD. किंवा जिथं बेंडिंग मोमेंट मॅक्सिमम आहे त्याच 2 पॉइंटला जर शिअर फोर्स 0 येत असेल तर दॅट बीम इज सब्जेक्टेड टू द प्युअर बेंडिंग कन्सेप्ट. Okay, so this is about the basic definition of the pure bending, or that pure bending is also called as a simple bending. त्यामुळे ह्या चॅप्टर मध्ये तुम्हाला एकच लक्षात ठेवायचं की द इफेक्ट ऑफ शिअर, मग शिअर फोर्स असू द्या किंवा शिअर स्ट्रेस असू द्या, द इफेक्ट ऑफ शिअर इज टोटली निग्लेक्टेड ड्युरिंग द बेंडिंग स्ट्रेस कॅल्क्युलेशन. Only this single sentence is sufficient. The effect of shear or shear force or shear stress is totally neglected during the bending stress calculation, and that we have discussed by using this particular figure, that is from portion B to C. B to C, bending moment is constant in BMD, but shear force is totally 0. So this is about the pure bending and the simple bending. Now, nature of the bending stresses. We have to study the two types of the beams, simply supported beam and the cantilever beam. But what will be the nature if the beam is subjected to the loading? So here what I will do, I will draw the figure for the simply supported beam. This is load W. This is load W. Okay. So this is the simply supported beam. Okay. And the center, what is the center of the simply supported beam is there. Either it is called as a center or it is called as a neutral axis. जो काय त्या बीमचा सेंटर पॉइंट आहे त्याला आपण सेंटर लाईन म्हणतो किंवा त्याला आपण काय म्हणतो, न्यूट्रल ऍक्सिस म्हणतो. सो दिस इज द बीम and it is subjected to the two amount of point loads W. Okay, so due to that particular point loads applied, what happened? The bending of the beam is taking place. Like see here. So the bending of the beam is taking place here. This is the cross section. So the cantilever simply supported beam is there. The simply supported beam is subjected to the 2 point loads which are applied in the downward direction. The figure number 1, this is the figure before loading. Figure number 2, bending of the beam is taking place. That means before loading the beam is perfectly horizontal. Figure 2 represents due to the load applied, the bending of the beam is taking place in the downward direction. And now please tell me, this is the center point of that particular beam, which is called as a neutral axis. If the bending of the simply supported beam is taking place in the downward direction, this particular simply supported beam is subjected to the two types of stresses. One is tensile and another is compressive. This particular simply supported beam is subjected to the two types of stresses. One is tensile and one is compressive. Now please tell me, where tensile stress is developed, above the neutral axis or below the neutral axis? Where compressive stress is developed, above the neutral axis or below the neutral axis? Now first we will think about the tensile only. Tensile stress is developed above the neutral axis or below the neutral axis after bending?
Below the neutral axis.
Below the neutral axis, everyone?
Yes sir. Yes sir.
बरोबर आहे. जो काय ह्या बीमचा सेंटर पॉइंट आहे त्या बीमच्या सेंटर पॉइंटच्या खालच्या बाजूला बीम इज अंडर टेन्शन. सेंटर म्हणण्यापेक्षा आपण त्याला काय म्हणतो, एक स्टँडर्ड वर दिला तो म्हणजे काय, न्यूट्रल ऍक्सिस, जो काही सेंटर लाईन आहे, सेंटर लाईन आपण काय म्हणतो, न्यूट्रल ऍक्सिस. इफ युअर सिम्पली सपोर्टेड बीम इज सब्जेक्टेड टू द लोडिंग, मग तो कुठला पण लोड असू द्या, पॉइंट लोड असू द्या किंवा युडीएल असू द्या, इट मे बी पॉइंट लोड, इट मे बी युडीएल, सेंट्रल ऍक्सिसच्या खालचा पोर्शन इट इज अंडर ऑलवेज टेन्शन, आणि ह्या न्यूट्रल ऍक्सिसच्या वरचा पोर्शन इट इज अंडर कॉम्प्रेशन. So this particular distribution is very, very important. And here, this is the cross section. This is the neutral axis. This is neutral axis. The upper portion of the neutral axis is subjected to the compression. This is only for the simply supported beam. Please keep in mind. And the bottom portion of the neutral axis is under the tension. And for that, if I have to draw the stress distribution diagram, अप्पर पोर्शन काय आहे, सिग्मा, म्हणजे हा झाला सिग्मा सी. बॉटम पोर्शन काय, सिग्मा टी. हा सिग्मा सी म्हणजेच हा एक प्रकारचा बेंडिंग स्ट्रेस आहे, लक्षात ठेवा. म्हणजे सिग्मा बी झाला. सिग्मा टी म्हणजेच हा पण एक प्रकारचा बेंडिंग स्ट्रेसेस आहे, म्हणजे तो झाला सिग्मा टी. नाउ प्लीज टेल मी, from this particular stress distribution diagram, where bending stress is maximum and where bending stress is zero. From this particular stress distribution diagram, where bending stress is maximum and where bending stress is zero.
न्यूट्रल ऍक्सिस ला 0.
From this particular figure, I can easily say that the bending stress is zero at the neutral axis or at the center point, but the bending stress is always maximum at the top of the beam and at the bottom of the beam. बघा ह्या टॉपला म्हणजे जो काय सिग्मा सी मी काढलेला, ही हॉरिझॉन्टल लाईन दिसते तुम्हाला. हा सिग्मा सी म्हणजे काय सांगतोय की सिग्मा सी म्हणजेच कॉम्प्रेसिव्ह स्ट्रेस, म्हणजेच तो काय एक प्रकारचा बेंडिंग स्ट्रेस आहे. म्हणजे टॉप पोर्शनला पण तुमचा बेंडिंग स्ट्रेस हा मॅक्सिमम असतो. तसंच बॉटम पोर्शनला पण ही हॉरिझॉन्टल लाईन वाढलेली दिसते. ह्या बॉटम पोर्शनला पण तुमचा सिग्मा टी म्हणजेच टेन्साइल स्ट्रेस, म्हणजेच काय तो एक प्रकारचा बेंडिंग स्ट्रेस आहे. म्हणजेच बॉटम पोर्शनला पण तुमचा बेंडिंग स्ट्रेस काय असतो, तर मॅक्सिमम असतो. मीन्स फ्रॉम दिस पर्टिक्युलर stress distribution diagram, I can easily say that the bending stress is always maximum at the top portion as well as at the bottom portion, but it is totally zero at the center point or at the neutral axis. And one more thing, in case of a simply supported beam, below the neutral axis, the beam is subjected to the tension, and above the neutral axis, the beam is subjected to the compression. म्हणजेच न्यूट्रल ऍक्सिसच्या वरच्या बाजूला जो काय स्ट्रेस येतोय तो स्ट्रेस कुठला असणार आहे, तर कॉम्प्रेसिव्ह स्ट्रेस असणार आहे. न्यूट्रल ऍक्सिसच्या खालच्या बाजूला जो काय स्ट्रेस असणार आहे तो स्ट्रेस कुठला असणार आहे, तर टेन्साइल स्ट्रेस असणार आहे. म्हणजेच युअर सिग्मा सी इज इक्वल टू सिग्मा टी इज इक्वल टू सिग्मा बी. सिग्मा सी म्हणजेच तुमचा काय असणार आहे, बेंडिंग स्ट्रेस असणार आहे, आणि सिग्मा टी म्हणजेच तुमचा काय असणार आहे, तर बेंडिंग स्ट्रेस असणार आहे. सिग्मा सी आपण हा फक्त कशाला इंडिकेट केलेला आहे, तर न्यूट्रल ऍक्सिसच्या वरचा पोर्शन हा कॉम्प्रेसिव्ह आहे, त्यामुळे त्याला आपण सिग्मा सी म्हणतोय. आणि न्यूट्रल ऍक्सिसचा खालचा पोर्शन हा टेन्साइल आहे, त्यामुळे त्याला आपण काय म्हणतोय, सिग्मा टी म्हणतोय. पण सिग्मा सी ला बेंडिंग स्ट्रेस पण म्हणू शकतो आणि सिग्मा टी ला पण आपण काय म्हणू शकतो, तर बेंडिंग स्ट्रेस म्हणू शकतो. अँड ऑलवेज your bending stress will be maximum at the top of the beam and at the bottom of the beam, but it is totally zero at the center point. Okay, so this is about the simply supported beam. Now next, second standard case, cantilever beam. So I will draw the diagram for the cantilever beam here. Let us see. This is the cantilever beam whose one end is fixed. This is the center line, neutral axis. Okay, this is the figure number 1 before load is applied. Okay, this is the figure number 1 before load is applied. After loading, what happened? The bending of the beam is taking place in the downward direction. You can see here. The W amount of force is applied. This is the figure number 2. Figure number 1 represents cantilever beam before loading. Figure number 2 represents cantilever beam after loading. Center point is called as a neutral axis. This is the cross section of that particular beam. Beam जर आपण समोरच्या बाजूने जर बघितला तर आपल्याला तो परफेक्टली रेक्टँगल किंवा स्क्वेअर दिसेल. Now please tell me, if the cantilever beam is subjected to the any type of load, maybe it is subjected to the point load or maybe it is subjected to the UDL, the bending is taking place in the downward direction. Please tell me the upper portion of the neutral axis, whether it is tension or compression.
Tension.
What about others?
Tension, sir.
Portion of the neutral axis, tension or compression? Tension. Right?
Tension.
It is tension. If upper portion is subjected to the tension, the bottom portion of the neutral axis is under the compression. Therefore, here it is capital T at the upper, capital C at the downside, and the stress distribution, once again, it is same. Again, this is sigma T, this is sigma C. Baga. If your cantilever beam is subjected to the any type of load, that load may be point load, that load may be the UDL, the bending of the beam is taking place in the downward direction. After the bending, that beam is subjected to the two types of stresses. One is tensile, another is compressive. And as we know that the nature of the stress for the cantilever, the upper portion of the neutral axis is under tension and lower portion of the neutral axis is under the compression. Therefore, at the top portion and at the bottom portion of the cantilever beam, again, the bending stress is maximum. This sigma T means your sigma B. Sigma C means your also sigma B. But at the center point, your bending stress is equal to 0. Therefore, from this particular two conditions, we can easily say that in case of a simply supported beam, in case of a cantilever beam, for both the types of beam, the bending stress is always maximum at the top portion as well as at the bottom portion, but the bending stress is always 0 at the neutral axis or at the center point. But only basic difference is there. In case of a simply supported beam, upper portion of the neutral axis is under compression and lower portion of the neutral axis is under the tension. But in case of a cantilever beam, exactly opposite. Upper portion of the neutral axis is under tension and the lower portion is under the compression. So what that particular stress distribution diagram? His stress distribution diagram तुमची काय इंडिकेट करे? बघा, वरच्या बाजूला एक हॉरिझॉन्टल लाईन आहे. ती म्हणजे काय? बेंडिंग स्ट्रेस वरच्या बाजूला मॅक्सिमम आहे. तसंच खालच्या बाजूला पण एक लाईन आहे सिग्मा सी. ती काय दाखवते? बेंडिंग स्ट्रेस इज मॅक्सिमम. आणि ही इन्क्लाइंड लाईन काय दाखवते? की टॉप पोर्शन पासून ज्यावेळेस तुमचा बेंडिंग स्ट्रेस हा सेंटरला जातो, एकदम टॉप पोर्शनला बेंडिंग स्ट्रेस इज मॅक्सिमम, त्याच्यानंतर मिनिमम 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 आणि ऍट सेंटरला तो काय होतो? मॅक्सिमम होतो. त्यामुळे बघा, ह्या फिगर मध्ये जर तुम्ही बघितलं तर हा झाला तुमचा टॉप पोर्शन ऑफ द बीम, हा झाला तुमचा बॉटम. ह्या टॉप पोर्शनला स्ट्रेस मॅक्सिमम असतो, तसंच ह्या बॉटम पोर्शनला पण स्ट्रेस मॅक्सिमम असतो. हा इथं मॅक्सिमम आहे एकदम एंड पॉइंटला. तो काय होतो? मधल्या पोर्शनला थोडा 0 होतो, परत 0 होतो आणि ह्या सेंटर पॉइंटला दोन्ही पण स्ट्रेसेस काय होते? एकदम 0 होते. त्यामुळं बेंडिंग स्ट्रेस हा ऑलवेज एकतर टॉप पोर्शनला किंवा बॉटम पोर्शनला मॅक्सिमम असतो, अदरवाइज इट विल बी 0 ऍट दी सेंटर पॉइंट. So this is about the basic nature of the bending stresses, and in this particular chapter only we have to study the nature for this particular two types of beams. One is simply supported, another is cantilever. त्यामुळे simply supported मध्ये please keep in mind upper portion of the neutral axis compression, bottom portion of the neutral axis tension. In case of a cantilever, upper portion of the neutral axis tension, bottom portion of the neutral axis compression. The stress distribution diagram for the simply supported and the cantilever beam, it will be same. What it indicates, top portion and the bottom portion bending stress is always maximum, but for the both types of the beams the bending stress is always zero at the center point, or it is always zero at the neutral axis. The sigma T and the sigma C, these are also your bending stresses, but in order to represent the tension condition, it is represented by the sigma T, and in order to represent the compressive condition, it is represented by the sigma C. So this is about the bending stress distribution diagram for the simply supported beam and the cantilever beam. Getting the stress distribution diagram for the simply supported and the cantilever, कुठला पोर्शन टेन्शन आहे आणि कुठला पोर्शन कॉम्प्रेशन आहे, आणि त्याच्या दोन्हीच्या बेंडिंग स्ट्रेस डिस्ट्रीब्युशन डायग्राम कशा आहेत. गेटिंग? Yes, have you understood this particular bending stress distribution
Yes,
for the
sir.
simply supported and the cantilever?
Yes, sir.
Yes, sir.
Okay. Now we'll take the last point, simple assumptions we will take, and then we will stop. So the assumptions made in theory of pure bending. What are the assumptions we have considered for the rotating shaft, the torsion of the circular shaft? In that also we have considered some of the assumptions. Similarly, we have to consider the assumptions in case of a pure bending. Whenever we are using the beam for the analysis purpose, whenever we are using the beam in any type of application, at that time that beam has to satisfy some of the standard conditions, and that conditions are called as a assumptions. So what is the first assumptions? It is represented here. The material of beam is homogeneous and isotropic. Homogeneous and isotropic, these are the two material properties. Whatever the material is used to that particular beam, maybe sometimes the beam can be prepared by using the maybe cement or some another construction material is there. Sometimes the beam can be prepared by using the metals also, because in case of a mechanical applications also we have to use some metal beams, and in case of a civil structure we are using that, we are prepared that particular beam by using that particular concrete structure. So whatever the material is used for that particular beam, that material should be homogeneous and isotropic. Isotropic means the material property of that particular beam, it will be same in all directions. For example, this is one point. This is one point. Here I am considering three directions. X direction is there, Y direction is there, and Z direction is there. In all the three directions, if material property is same, for example, E in X direction 200 gigapascal, E in Y direction again 200, E in Z direction again 200. That means in all the three directions, if your material property is same, then I can say that that material is isotropic. What is the definition of isotropic? If the material property of that particular beam is same in all direction, that beam will be the isotropic. Then what is meant by the homogeneous? As we know that the beam can be prepared by using the number of particles. एकाच beam मध्ये number of particles असतात. सगळे particle एकत्र होऊन एक structure तुमचं काय होतं, फॉर्म होतं. जर प्रत्येक पॉइंटला जर material property same असेल, number of points are present or number of particles are present in that particular beam, for each and every particle, if material property is same, then that material is homogeneous also. Isotropic property ही फक्त मी एकाच पॉइंटला एक्सप्लेन केली आहे. म्हणजे एखाद्या पॉइंटला किंवा एखाद्या पार्टिकलला तिन्ही डायरेक्शन मध्ये जर मटेरियल प्रॉपर्टी सेम असेल, तर ते मटेरियल आपण काय म्हणतो, आयसोट्रॉपिक म्हणतो. असंच बीम मध्ये नंबर ऑफ पार्टिकल असतात, नंबर ऑफ पॉईंट असतात. कारण नंबर ऑफ पार्टिकल कंबाईन होऊनच तुमचं एक स्ट्रक्चर काय होतं, फॉर्म होतं. अशा नंबर ऑफ पार्टिकलला फॉर एक्झाम्पल 1000 पार्टिकल असतील, 1000 पॉईंटला किंवा 1000 पॉईंटला किंवा पार्टिकलला जर मटेरियल प्रॉपर्टी तिन्ही डायरेक्शन मध्ये जर सेम असेल तर दॅट मटेरियल इज कॉल्ड ॲज ए homogeneous. Therefore, this homogeneous and isotropic property is related to the property of material in all the direction. The second assumption is the beam is perfectly straight before loading or after bending. Before bending or after, before loading. Beam should be perfectly straight without application of load. If beam is already in bending condition, I have not applied any point load, I have not applied any UDL, then also bending of the beam is already taking place, then that particular beam should not be used for the analysis or it should not be used for any type of application. Therefore, before loading, before bending, the beam should be perfectly straight. If it is perfectly straight before loading, after bending no problem, after loading no problem, the bending of the beam is taking place because load is applied. But before loading, before bending, beam should be perfectly straight. So this is the second assumption. Third, it has uniform cross sectional area throughout the length. For example, here I will draw one structure perfectly horizontal. It is having the uniform cross-sectional area. So whatever the cross-sectional area is present at the left side, same cross-sectional area should be at the center point. Same cross-sectional area should be at the right side. So from left to the right direction, the cross-sectional area of that particular beam should be uniform. म्हणजे लेफ्ट साइडला cross-sectional area for example 400 mm square असेल. If beam is considered as a circular, सेंटरला पण किती पाहिजे 400 mm square, राईट साइडला पण किती पाहिजे 400 mm square. That means from the left side to the right side, the cross sectional area of that particular beam should be perfectly straight or it should be perfectly uniform. Therefore, the third assumption indicates it has uniform cross sectional area throughout its length from starting point to its end point. The cross sectional area should be uniform, as well as at the center point also the cross sectional area should be uniform. Okay, this is the third assumption. Fourth assumption, the beam is subjected to the pure bending only where the effect of shear neglected. We have discussed that pure bending concept. We have seen that particular BC portion in bending moment diagram and that BC portion in the shear force diagram. In bending moment diagram, the BC portion represents the constant bending moment. But if I will observe same BC portion in the SFD, the shear force is totally zero. Means I can say that the beam is subjected to the constant bending moment only where the effect of shear is totally neglected. किंवा जिथं बेंडिंग मुवमेंट मॅक्सिमम आहे त्याच पोर्शन मध्ये शियर फोर्स हा तुमचा काय असला पाहिजे 100% 0 असला पाहिजे. मीन्स युअर फोर्थ assumption will be satisfied. The beam is subjected to the pure bending only. मग बीम हा प्युअर बेंडिंग कधी असेल किंवा सिंपल बेंडिंग कधी असेल, जर एखाद्या पोर्शन मध्ये बेंडिंग मोमेंट हा कॉन्स्टंट आहे पण त्याच पोर्शन मध्ये जर शियर फोर्स हा 0 असेल, then only the beam is subjected to the pure bending. Means the effect of shear is totally neglected. This is the fourth assumption. Then fifth, the value of Young's modulus is same in tension and compression. We have discussed the nature in the last two figures. Nature of bending stresses for the simply supported beam and nature of bending stresses for the cantilever beam. In case of a simply supported beam, above neutral axis compression, below neutral axis tension. In case of a cantilever beam, above neutral axis tension, below neutral axis compression. But even your beam is under tension, even your beam is under compression, the value of Young's modulus should be same. बीम मध्ये टेन्साइल स्ट्रेस आलाय म्हणून त्याचा यंग्स मॉड्युलस हा चेंज होत नाही. बीम मध्ये कॉम्प्रेसिव्ह स्ट्रेस पण आलाय त्यामुळे त्याचा यंग्स मॉड्युलस चेंज होत नाही. इवन युअर बीम इज अंडर टेन्शन, इवन युअर बीम इज अंडर कॉम्प्रेशन, द यंग्स मॉड्युलस मीन्स कॅपिटल ई, इट शुड बी सेम इन टेन्शन इन कॉम्प्रेशन. बीम मध्ये टेन्साइल किंवा कॉम्प्रेसिव्ह स्ट्रेस आल्यामुळे त्याची मटेरियल प्रॉपर्टी चेंज होत nahi. Material property of that particular beam, it should be same or it will be remain same in tension or as well as in compression. That is the fifth assumption. The Young's modulus म्हणजे काय असतो तुमचा कॅपिटल ई. कॅपिटल ई म्हणजे काय सांगतोय, इट इज द मटेरियल प्रॉपर्टी अँड दॅट मटेरियल प्रॉपर्टी विल बी सेम इन टेन्शन अँड इन compression. And last assumption is called as a it obeys the Hooke's law. It obeys the Hooke's law. Whatever Hooke's law states that within elastic limit the stress is directly proportional to strain. ज्यावेळेस आपण एखाद्या बीमवर लोड अप्लाय करतो त्या लोडमुळे त्या बीम मध्ये काहीतरी बेंडिंग मुवमेंट जनरेट होतोय आणि तो बेंडिंग मुवमेंट जनरेट झाल्यामुळे त्या बीम मध्ये एक प्रकारचा स्ट्रेस इंड्यूस होतोय. तो म्हणजे कुठला, बेंडिंग स्ट्रेस इंड्यूस होतोय. ज्यावेळेस त्या बीम मधला बेंडिंग स्ट्रेस हा वाढत असतो त्याच वेळेस त्या बीम मधला बेंडिंग स्ट्रेन पण तुमचा काय झाला पाहिजे, वाढला पाहिजे. बेंडिंग स्ट्रेन वाढतोय म्हणजे काय होतोय, त्याचे डायमेन्शन चेंज होते. बिकॉज स्ट्रेन पॅरामीटर इज रिलेटेड चेंज इन डायमेन्शन. पॅरामीटर इज रिलेटेड टू द चेंज इन डायमेन्शन. त्यामुळे ज्यावेळेस आपण बीमवरचा लोड वाढवतोय, लोड वाढला म्हणजे बेंडिंग मुवमेंट पण वाढला, बेंडिंग मुवमेंट वाढला म्हणजे त्या बीम मधला बेंडिंग स्ट्रेस पण वाढला. बेंडिंग मुवमेंट वाढल्यामुळं त्या बीमचं मॅक्सिमम बेंडिंग व्हायला लागलं. बेंडिंग व्हायला लागलं म्हणजे काय झालं, त्या बीमचं मॅक्सिमम डिफॉर्मेशन व्हायला लागलं. म्हणजे बीमची चेंज इन लेंथ काय व्हायला लागली, इन्क्रीज व्हायला लागली. मीन्स इट ओबेज द Hooke's law. Means due to the increase in load on that particular beam, the bending stress is directly proportional to the bending strain. Because whatever Hooke's law states that within elastic limit the stress is directly proportional to strain. Similarly, if your beam is subjected to the loading, if bending stress is increases, at that time the bending strain is also goes on increasing due to the increase in bending moment. So these are the 6 assumptions which we have to satisfy while using that particular beam for the analysis purpose or for the any type of application. जर तुमचा बीम हा परफेक्टली स्ट्रेट नसेल, त्याचा क्रॉस सेक्शनल एरिया युनिफॉर्म नसेल, त्याचं जे काही मटेरियल प्रॉपर्टी आहे तिन्ही डायरेक्शन मध्ये त्याच्या मटेरियल प्रॉपर्टी सेम नसतील. एक्स डायरेक्शन मध्ये 200 आहे, वाय डायरेक्शन मध्ये 150 आहे, झेड डायरेक्शन मध्ये 220 आहे, म्हणजे आयसोट्रॉपिक मटेरियल प्रॉपर्टी सॅटिस्फाय होत नाही. आयसोट्रॉपिक जर सॅटिस्फाय होत नसेल तर तुमची होमोजिनियस प्रॉपर्टी पण सॅटिस्फाय होत नाही. किंवा टेन्शन मध्ये आणि कॉम्प्रेशन मध्ये जर तुमचा यंग्स मॉड्युलस चेंज होत असेल तर इट इज नॉट ऑल्सो एक्सेप्टेड. मीन्स इट इज नॉट पॉसिबल टू यूज such types of the beam for further analysis. If your beam will satisfy all these particular 6 assumptions, then and then only that beam I can use for the further analysis or it can be used for your further application. So these are the assumptions made in the theory of pure bending. जसं shaft ला आपण assumption consider केले होते, the material of the shaft is homogeneous isotropic, the shaft should be perfectly straight, the cross sectional area of the shaft should be uniform. Similarly, we have to consider the assumptions for the beam also. So these are the 6 assumptions. If beam will satisfy these 6 assumptions, we can use that particular beam for the further analysis or further application. If beam will not satisfy these particular assumptions, it is not possible to use that particular beam for further analysis or for further calculation of the bending stresses. So these are the assumptions made in the theory of pure bending. Based on this particular assumptions, 101% one MCQ question will be there. So you have to remind this particular all the 6 points and you have to choose your correct option. Okay, have you understood this particular assumption? Same assumptions which we have considered for the shaft, but here we have considered for the type of beam. Okay, Have you understood these particular assumptions?
Yes, sir.
Okay. So with this, today we will stop here. So what we have covered in this particular new chapter, we have started with the basic introduction related to the bending stresses, how to calculate the bending stresses by using the bending moment for these 4 standard cases: simply supported beam with point load, simply supported beam with UDL, cantilever beam with point load, and cantilever beam with UDL. So for these 4 standard cases, we have to calculate the bending stresses. Then we have discussed about the nature in case of a simply supported beam, where it is subjected to the tension or compression, and in case of a cantilever beam, where it is subjected to the tension or compression. Therefore, this neutral axis, position of the neutral axis, it is very important. In addition to that, in case of a simply supported or in case of a cantilever beam, in both the types of beam, the bending stress is always maximum at the top portion as well as at the bottom portion, but the bending stress is always zero at the center point or at the neutral axis. And last, we have discussed about the 4 assumptions which that beam has to satisfy. If it is satisfied, then we can use that particular beam for the further analysis or for your further application. So this is about the assumptions. So with this, today we will stop here. Remaining part we will take in the next lecture.